Well, g'day everyone. Here we are on another Sunday afternoon Toolbox Tech Talk with me, Glenn Morris from the Smart Energy Lab. Wow, it's been a week. Look, I'm going to do things a little bit differently today. I've got a guest which I'll introduce in a minute, and I think many of you may well have seen the promo for that. But first up, I'm going to do a little bit of show and tell, sort of the things that turn up in the lab all the time. So a lot of companies send me product to review, to play with, to get to know, to share with my students, and I really appreciate that. Some of the things that turned up this week in the lab is, we'll start from the smallest, see if I can reach down and grab it, is from SunGrow. Now, I've got a little overhead camera which I can kind of flick to so you can see what we're looking at here. So there's a little overhead. This is a 4G modem designed for remote monitoring of inverters. So this little thing here comes with antennas as well. I think I've got those here. Oh yeah, I should have actually put them better in reach. I dropped the antenna, but it comes with a magnetic base, some cable, an antenna, and it's got the relevant ports on the bottom here. So we've got our LAN port, and then we've got a WAN CON port power. I believe it's powered from, there's a brick here with it, but I think it's a 12-volt supply. So the idea of being able to monitor stuff without using the customer's own Wi-Fi, that's a big plus. And this is kind of a device that you might use where the customer has either no local internet, but you still want to monitor it. Anyway, that's the little 3G modem for SunGrow. And I've got some bigger stuff here. Hang on. Well, I didn't organise my desk very well. Now, this is not new. This is old. I just want to show you what's happening in the DC isolator world. Now, what you're looking at here is a HRC fuse switch. Now, these have served us well for a long, long time as a means of isolating high current DC, and they've got a fuse and a disconnection mechanism, and they're very, very sturdy. They can hold, this is a small unit, it goes up to 160 amps. As you can see, it's quite dusty. It's an old one. I just pulled it out of the storeroom, and the mechanism requires quite a bit of force to shut. And that's one of the problems when you give it to a customer, is they don't shut them properly. But the big problem we're having now is that new battery standard mandates that DC isolators used indoors for battery systems need to be IP23 as a minimum. And written on the front here, you probably can't see it, is IP20. So as it is, this doesn't comply because of its IP rating. Used in circuits below 60 volts, the access of live parts is acceptable, IP2X. But once you go to IP23, it's about dust and other environmental ingress. So you need to go to something that's got a proper rating. So we've got something here. Whoa. Now, it's pretty big, so I'm just going to switch cameras so you can see me holding it. Oops, wrong one. Here we go. So this is a battery DC isolator built by CBI Electrical, and it's in a IP, geez, it's probably 68 until you put a gland on it, but it's IP 60 something. And inside they have a range of sizes. This is the 250 amp version, so it's 4-pole. It's lockable in the off position, so there's a lock dog mechanism here, so it can meet the requirements of our battery standard. And it's got a rubber door seal, as you can see around here. So this unit can be drilled out and glanded to, it's also got a hydrophobic plug. Means it's scared of water. Well, actually, it just means it will release water, but it won't let it ingress. It'll also let moist air out, so it won't cause condensation. So this is a high level. This is way more than IP23, but if you're using a battery system outdoors, you're required to have IP56, no water. So this meets that requirement. So this is suitable for outdoors. Got one more thing coming up. Let's have a look. All right. There's a lot of stuff in this box, but basically it's the SMAPI monitoring system. We haven't actually installed it yet. We're just going through the manual at the moment with my electrician, making sure we understand all the components. So it's got CTs, it's got a smart dongle, it's got devices for measuring water. Check it out. It looks like a frog. This little thing here actually clips over a pipe and can be used for measuring water flow or gas. And it's got a brain as well. So it's one of these boxes contains the brain. It can measure appliances as well. So look, here we go. This little bulby thing transmits. And so you can plug an appliance into this and it will transmit the consumption data of that appliance. So that's their SMAPI switch. And then we've got a whole bunch of CTs. So I think we've gone for the 3-phase system here. These are, oh no, that's the smart device. So this is for communicating digitally. And so the mains comes in here, it measures voltage and it communicates. So there's a whole bunch of components there. I'm not doing a very good job packing it up. And here's the frog. Oh, I just love the frog. Check it out. So there it is. That's the gas and water metering device. So actually clips over the pipe like this, see? And lops onto it. So it must have a sensor in here that can measure flow and it communicates that digitally. So that's the gas and water. And then we've got the energy component for energy monitoring of your house. This one's got a few more layers to it. I'm really going to have to tidy up after this. So here we go. And so that's the house energy monitoring device. I think this is also a display by the look of it. I'm going to actually install this and do a full presentation of the product here at the lab. So this is just showing you some of the stuff that turns up, and then we've got to sit down and read the manuals, talk to the suppliers, find out how to install them. I think I've got one more in here somewhere. Here we go. Oh no, these are more CTs. So they sent me a lot of CTs for monitoring different circuits. So we've got a whole box full of CTs there. So anyway, that was a little bit of show and tell from CBI Electrical, from SunGrow and from SMAPI. Anyway, so today I'm going to introduce my guest. And look, I first met our guest today many years ago, I think over 10 years ago, when he was on one of my courses. He's, euphemistically rattled around the solar industry and has built some of the biggest and some of the smallest things in the industry. He also ran one of the biggest solar installation companies in Victoria, but now he's broadened his horizons, and he also does passive house design as well as energy storage products and development of products with his company RVO. So it's my pleasure to welcome Paul Wilson to Toolbox Tech Talk. Let me bring you out of the green room, Paul. Here we go. Okay. Hi, Paul. I've still got you muted. It's the old story. Press the unmute button. And then I've got the spinning wheel of death on the unmute button. But Paul will suddenly come out of mute land in a moment once we get him back here. And we're just getting a little bit of a delay in my software. Sorry, everyone. Looking a little bit frozen here at my end. So I'm just going to ignore that. These things happen. And while we're doing that, I'm just going to check out that we actually are going live. Here we go. So, Paul, are you with us?
I'm with you. I'm not on the screen with you, but I'm talking.
There we go. Got you back. So that was a bit of fun and games at my end. Part of Toolbox Tech Talk, Paul, is it doesn't quite work properly sometimes. So here we are. So how's it going, Paul?
Great. Thanks, Glenn.
Have you heard the news today from Dan Andrews?
I hear it through my kids saying, I think we can go 25 kilometres away from home now. I think that's the latest.
Yep. And as far as the solar industry goes, it's really good news. It's official. 5 installers can go to site as long as they're working outdoors. So that means solar's back on in Metro Melbourne from midnight tonight. So that's a big relief to all those Metro Melbourne installers. So how have you been filling your days, Paul?
Well, we've been working a lot of hours. We've been developing quite a few new products to add to our suite of products. Our most recent one, which is going into production next week, is the 147 volt UCB, which is a very high powered, fast charging, long life battery. And we've been developing the Emax platform, which is one that speaks with Electronic, which a lot of you know about already. And it also now speaks to microgas turbines and air conditioners and security cameras and a few other extra items. So, and very soon to speak to the batteries as well on a cell level. So the one platform can allow people to see the inverters and the cells and the fans and the temperature and everything in one web page.
Wow. So you're doing almost whole of home monitoring or installation monitoring now.
Yeah, well, the aircons is a bit of a given because we're building a 20-foot containerized solution now, and to view and control the air conditioners is obviously useful, and to see the temperature of every battery and every cell voltage is very useful as well. So it sort of just was a natural progression to add them all to the same platform.
Great. Well, just before we carry on, I just want to welcome all those who've come and joined us via Facebook, YouTube, and even Twitter. You're welcome to ask questions. This is a live event. We love having questions. I can bring your question up on screen, and so you might want to check spelling and stuff before you post it. I'll bring it up on screen, and then people, myself or Paul, can answer it. Yeah, feel free to do the usual things. Press the old like button in YouTube land and in Facebook. So that much appreciated. So back to Paul. Paul, not everyone would know Avio. Give us a little thumbnail sketch of you and your company.
Okay, so we've been developing software for about 9 years now, and installing on-grid, off-grid hybrid solar power systems using originally lead-acid batteries. And then we moved on to a product from Dubai called Kilowatt Lab Supercapacitor Battery. And now we still sell that product, but we also now developed our own product line called the UCB, which is the ultra capacitor battery. So we develop software and we build energy storage systems. And we also have part of our company does passive house design and construction. We've only built maybe 3 or 4 homes so far, but they're all built to the passive house standard, which is the official German standard for super efficiency. So it all has this very efficient longevity design. So that's a bit about Avio.
Right. So it's passive house is much more than, just throwing some insulation in the roof and put double glazed windows in.
It is. It's actually an engineered solution. As you can imagine, the Germans are very methodical. One of the rules for a passive house certified outcome is to remove 90% of the heating and cooling load, not just reduce it a little bit, but it's actually 90%. And we have to get down to about 10 watts per square meter of heating and cooling plant rather than 100 watts, which is what's on a typical home. So
wow.
Consequently, you can run a home really easily on solar power because you have almost no heating and cooling loads, which is your biggest natural load on a building.
Look, I really love energy efficiency. It's often referred to as the first source of energy is efficiency, because it is free. And it does reduce the cost of everything. So yeah, that's a really good place to start, in my opinion. So Paul, go ahead.
No, we just figured that if we can make a super efficient building and then put a very large energy system on it with lots of PV and lots of storage, then that's enough to run the vehicle as well. And that way you can take the vehicle off the petrol grid.
Like you have yourself.
I have for 5 years now. It's been a good little car, that wishy.
Well, I hope to be joining the EV revolution soon. So yeah, it's totally time to do it. Paul, so I promoted this Toolbox Tech Talk focusing on the ultra capacitor battery. Now, there's going to be all sorts of questions about this probably, so feel free, everyone who's watching, to type in your questions. But look, the elephant in the room is really, is it really a capacitor or is it a battery? Do you want to just tell us that one?
Sure. Well, there is controversy around this. If you do your own homework, you'll find that there are around 7 different supercapacitor and ultracapacitor and hybrid capacitor batteries in the supercapacitor family, and this is one of them. So there's electrostatic storage and there's electrochemical storage, which means it's not a pure capacitor like some might say, but it's also not just like a battery, which is a very different product when you compare it to the outcome of this product. So probably better just to read your own white papers. There's plenty of them to read. This particular technology started in South Korea, and there's white papers you can read about why it's called a supercapacitor and where that's derived from. But really, probably the main question is, does it do what a supercapacitor does? Does it last as long as a supercapacitor does? And the cycle testing we've been doing so far is projecting out to around 35,000 cycles, which is what often capacitors are touted to do. And the charge rate is extremely fast. We've got a 6-minute charge and 6-minute discharge. And you can even peak at 3 minutes charge rate for 10 seconds, which is 20 C. So it behaves like a capacitor, it looks like a capacitor, and it lasts like a capacitor, and has capacitive effect, but it also has a lot of battery properties, which has a voltage curve like a battery, and it charges like a battery and performs like a battery. So we call it an ultracapacitor battery because it's got a bit of both. The balancing system we use.
So hang on, just interrupt you for a moment. So let's call it the UCB for short. It's actually your development, your product?
Yes.
Yeah, so I'm curious, why did you choose to develop your own storage solution as opposed to buying an off-the-shelf one?
We couldn't find anything that would give us extremely high peak power and longevity and extremely high round-trip efficiency. So we were really concerned about, it's kind of like a passive house where if you can get rid of all the losses and make it last a really long time, it's worthwhile spending the extra money. And so we thought, let's design a battery that can last more than 20 years. That helps with recycling, because if you have a battery that lasts 5 years or 8 years or 7 years, then you have to deal with it in that short amount of time. And a lot of batteries in the market would only really just pay for themselves by the time they'd expired, which kind of meant it was a bit of an arguable thing to put one on a hybrid system on grid, for example, because there was no real financial benefit. So we needed to make a battery last much longer and have much more power, so it could run a home in complete off-grid mode if you needed to. Like, for example, with a hybrid system that has to run the whole building in a blackout.
Right. We've got a question in here, and let's bring it on screen from Bradley Patton. He's interested in a link to the white paper. Now, I presume this is something we can put in the comments later on. I don't want you to have to go and look it up right now. But there's obviously people who want to do the research. So thanks for that one, Bradley. We'll follow that one up. Yeah, so you developed the UCB.
Just to clarify, you do have to pay for the white paper. It's not free. So, yep, I'll provide you the link. You go on there and you download it from a science website.
Fair enough. I mean, academics these days have to earn their keep even more than they did before. Writing research papers. So you developed the UCB for Avio for your own use. Has it got a particular application at the moment in terms of the market where it's being used?
Yeah. We're using a lot of off-grid projects. Obviously, most people who build off-grid build for a long haul. They don't build for short term. So having a battery with a 20-year design life is a very big plus. We're also using it in UPSs. So we've done a few schools so far where they wanted a lot of energy and a lot of power to back up their school server rooms in the event of a blackout. A lot of schools are in remote areas and in fringe of grid, and consequently, if they lose their servers, they lose their connectivity for all their teachers and students, which is a big problem with the current remote learning issues. We've done mobile jobs, houseboats, remote area jobs. We're about to do a coal power station, so we're solar powering a coal power station's admin and workshops.
Is there a certain irony to that from the customer?
I just love the idea of this project just because of the fact that it's a coal power station, and half a kilometre from the solar power system is a coal pit. And the reasoning, the logic is that the whole site runs on a diesel generator, and it's too far to run a cable from the generator, the coal generator, to their admin buildings to make it economically viable. It's cheaper to do solar. So probably the first solar powered coal mine in Australia.
Yeah.
I think.
So I think you could pitch that to the PR people as you're providing them with reliable base load.
That's right. And they run those enormous compressors that pump up the gigantic tyres on those dump trucks. So they've got a huge startup current, so they need a lot of peak power. And that's where the UCB really wins out with peak power.
Yeah, cool. Well, look, we've got a bit of a treat for the audience. He's really good at doing 3D CAD, and Paul's going to pull apart one of his UCBs virtually on screen. So I'll give Paul a chance to get that ready, and then we'll share his screen so you can see what's inside it, and Paul can explain how it works. So, Paul, do you want to bring up your shared screen? I'll bring it on when you're ready. You ready now?
Yeah,
okay. Here we go.
So this is the latest Titan 147 6 kilowatt hour. So it's 6 kilowatt hours of storage. It weighs just under 100 kilograms, and it stands upright on the floor, or you can lie it on this short side here. So you could lie it down on a rack and have a row of them. The product is designed to charge in a short period of time. It's got a built-in molded case circuit breaker in the top, which is 250 amps. And so that's this guy here. It's got a centrifugal fan here as well. The centrifugal fan is used to pressurize the vessel with fresh air if we are running at really, really high rates of charge and discharge. All of the bus bars are made of solid copper, which is Cu 1220 copper. Typical cross-sectional area is about 100 square millimeters for all the copper parts inside. And we've got here balancing boards with pure supercapacitors on them, as opposed to the hybrid supercapacitors in here. So these balancing boards have got two pure supercapacitors on them, which do the equalization between the cells. And we've got a board here, which is developed by Avio, which is the power supply board, fan control board, and Modbus to Ethernet board. And then can
I slow you down for a second? So sure. I was doing a bit of screen rearrangement then, which may have interrupted some of your pull-offs there, but we're good now. We're both on the screen. I can see you over there, and you can see me, and everyone can see the UCB. So you were just assembling it piece by piece. Now I note before we went on air, I was asking about those connectors, and they looked a lot like Amphenol connectors because previously used solid copper bar. Why the change?
That's right. Because we're into the sort of unsafe voltage range at 147 volts nominal, we're using these touch-free connectors here, which are rated to 350 amps. So if we look at the actual calculations here, can you see that spreadsheet okay, Glenn?
Yes, that's fine.
Yeah, on the right column over here, you've got 6 kilowatt hours of energy storage, 250 amp MCCB built in, and a peak charge rate of 36.8 kilowatts. So that's before the circuit breaker trips. And we did that just to try and get some control because it's otherwise too powerful for most applications, and you start to have other issues when you start to parallel too many of them.
How many battery modules is that?
That's one. So
it's 6 kilowatt hours, that one battery module, and 36 kilowatts of power.
Yes. If we take the circuit breaker out, or if we increase it, we can also do a 500 amp circuit breaker. Or if we take it out completely, we hit 117 kilowatts peak. And that's continuous supply, as in that's the peak of the continuous rate of charge and discharge, which is a 6-minute rate. And yeah, it's a very, very powerful battery, but you don't need that much power normally. Normally you need more energy before you need that much power. So we've constrained it to 36.8 kilowatts. And then you just keep paralleling them until you get the amount of power you want and energy you want.
Gotcha. So going back to your pull apart. Oh, that's the fan, sorry. Yep.
Yeah, that's the fan. That's a centrifugal fan. We use a centrifugal fan rather than an axial fan because centrifugal fans can create more static pressure, which is much better for weaving air through the tortured path through the battery.
Right.
We go across to here. We've got
that looks like the sort of fan you see in a laptop computer. Is that a centrifugal fan?
Yeah, that is. But they are, and the reason they're that shape is because they need to pressurize the air through the laptop whereas an axial fan can get good airflow, but it doesn't have a lot of pressure. There's two components to a fan's airflow. This is
Gotcha.
the PoE board here. So the balancing system is actually powered by a PoE switch, and we did that so that
You
balancing
better
system.
expand that acronym for people who are not familiar with IT terms.
Okay, so PoE is power over Ethernet. And instead of powering the balancing system from the battery, we actually power it from a remote PoE switch, which is just a typical Ubiquiti switch or Cisco switch or D-Link switch. And that gives us the ability to turn off and on the balancing system. It also gives us a path for the data. So we've got cell level monitoring. So I'll pull up that on the screen. Here we go. This is a live login to one of our cycling cells at the moment, cycling modules.
Is that a 24-hour period?
Yeah, that's 24 hours. So we're cycling it, charging it and discharging it every hour. And we've been doing that for 4 months now at this rate, which is simulating 4 years of use. And after 4 years of simulated use, we've had no degradation of capacity. And that's at 1C or C1. You can say it both ways. You can see we're keeping it really hot too. So we're keeping it at 47 or 45 degrees Celsius. And on the way down, when it's emptying, it's getting cooler and it falls down to 43 degrees. So we're keeping it really hot to simulate a bad environment, like a remote hot environment. And we're charging and discharging every hour. So I can go back to a previous week here. It looks quite funny when you see a week. It's a week of charging. And I go back to a previous month.
Wow, you're really thrashing it. I don't suppose you have one of those cells lying around on your desk, do you?
No, I don't have one here. No, sorry, I'm at home.
Oh, yeah.
You can see if I pull up the actual cell level monitoring here.
Yep.
You can see at the bottom of this graph, you can see I've got the voltage of every cell inside the pack here as well. So we're sitting at average of 2.6 volts, 2.64, 2.65 volts per cell.
So you're monitoring at a cell level?
Yeah, every cell, every module, every temperature in 3 locations in the pack.
Yep.
And because of all of this monitoring that we do remotely and all the remote alerts we've been able to extend the warranty out. So we're offering a 20-year warranty for people who accept a maintenance plan, which includes a monitoring fee. And because we can see the health of every cell and every module for the life of the product, we could preemptively maintain a product. If there was ever to be a fault, we'd see it occurring well in advance.
Yeah. Oh, that's such a good feature. I mean, I think more and more with IoT, products are starting to self-diagnose and run alerts. I mean, it's nice if your car tells you your brake pads are just about to be worn out before you have to get new discs.
That's right. This is an interesting one here. If you have a look on the green and the grey shaded areas, you'll see that they're little steps. So the green area is energy in, so it's energy filling up the module. So it's flatlining in that section there, so it's not moving at all. It's staying at 3.814. If you can see that clear enough, I'm not sure. Maybe I'll zoom in a bit.
Yeah, that's good.
Okay. Yep.
Great.
And then we move up a step. We're at 5.783 and move up a step, 7.752 and so on. And we look at the grey area, that's the energy out. That's what we're deriving from it on the discharge. So at 3.814, it's flatlined. We discharge it up to 5.660. Now, if you put that into a spreadsheet and you calculate the energy in and the energy out, and you take an average of, say, 24 hours, we're losing about just over 1% of the energy in a full cycle, which is down and up. So the round trip efficiency, I think, is around about 98.57% round trip. So we're losing just under 0.75% in each direction, which is really good from a performance point of view. But it also helps a lot in a 20-foot containerized version because there's almost no heat dissipated, which means you need very little cooling for your shipping container.
Right.
So energy efficiency has got a lot of knock-on effects.
So you're building larger units, the shipping container sized?
Yeah, well, it's including 250 kilowatt hours of storage using this module.
Wow.
So there's 42 of these modules inside the container, along with 6 SP Pros, the 1202, which is the 20 kilowatt model, and we're hitting 214 kilowatts peak AC and 120 kilowatts continuous AC from the inverters, and the battery energy storage of 250 kilowatt hours is, from a power point of view, on a DC side, you're looking at 42 times 37, which is an astronomical number. I think it's 2 megawatts of DC power available if you needed it. Not that you would need that, but it's available.
Maybe the coal mine does for its compressors.
Well, the startup load on the compressors is, I think, around about 140 kilowatts.
Wow.
So having that up the sleeve is really important. So we're doing a power chain solution there to give it the peak AC.
Yep. Can we just pause for a moment, Paul, because people are joining as we go through this live. Just like to welcome those who've joined via Facebook, YouTube, and Twitter. It's good to have you. Please feel free to ask questions in the comments area. So if you've got that accessible to you, and I can bring your comments on screen and we can answer them. So just check the spelling before you bring them on screen, and there'll be the little icon associated with your comment will come on as well. Yeah. So Paul, just in terms of size, what are we looking at there? Is that like a pocket size thing?
This is well, if I go back to here again, the dimensions are right here, which is 213 by 486 by 788. So, yeah, size of a shoebox, and then the height of a cricket stump. There you go.
That's great. I love it. A shoebox extended to the height of a cricket stump, and with the power of a car. Yeah.
The power of many, many horses. So 37 kilowatts is about 25 or 30, 40 horsepower or something. I'm not sure exactly.
Wow. Okay.
If we run it very hot, so one of the tests somebody asked me to do was, well, it's all well and good to say it's going to run 25,000 cycles, but what if it's really hot? So that's why we're running that test module at 45 degrees Celsius. If you're under the 55 degrees Celsius, the design life is only 4,000 to 6,000 cycles, which is about 15 to 17 years. But not many people would need to run it at 55 degrees 24 hours a day. That'd be pretty rare. So we figured we'll test it at 45 degrees Celsius, which is probably the hottest it's going to be anywhere. And then we'll do it continuously at that rate at 1C, and we'll see how much degradation we get, at the 5-year mark and the 10-year mark, the simulated 5-year and 10-year mark. At the moment, we're only up to 4 years simulated because we've only been cycling at that high rate for 4 months.
Right. So let's go back to that picture. So you took the cover off the UCB and you were showing us what's inside.
Yeah. Just pull it up again. Hold on.
That's it.
So there's 64 cells in there, and I'll just turn it here again.
So this is the 140 something volt unit. Is that what you're describing?
It's 147 volt nominal.
Yep.
So its voltage charge window is from 100 to 170. That's the tolerable window.
Yep.
But the nominal voltage window that we recommend you use is about 110 to 165 volts. So you couldn't overcharge it with an SP Pro because it can't go over 170. The SP Pro can't charge past 165. You can DC couple with it, we did a project recently where we DC coupled 20 kilowatts of PV to the 120 volt bus or 145 volt bus. So your voltage window here, upper limit here is really 179 volts is allowable. The design range is 166. The nominal is 147, and the very bottom we don't want you to go below is 96 volts, and 115 volts is the recommended cutoff.
So given the
quick charge.
Given that you can go to 179 volts, but say connected to an SP Pro, you can't even get there. How do you balance these cells? Like normally they use top balancing, so they require to go near their full voltage.
We balance with supercapacitors. So it's like bailing a boat out, effectively. So we fill up a pure supercapacitor with the surplus energy from the highest voltage cell, and then we dump that into the lowest voltage cell. So if I pull up this here, the cell level, I'll just do this 12 cell level monitoring. It's probably the cleanest view. I'll zoom out a bit. Okay, so you see here the cells are all around the same, 2.348, 2.372, and so on.
Yep.
So we basically take the highest cell in the pack and then we fill up the supercapacitor, the pure supercapacitor, and then we look for the lowest cell and we empty it into that cell. And then while that's happening, we're filling up another supercapacitor with the highest cell and emptying into the lowest cell. So we're continually bailing out of the highest cell into the lowest cell. The rate of balancing is only 2 amps. So if you get to the highest, when you get to almost full, if you're charging really hard, when you get very close to being full on the battery side, then we can send a signal out and tell you to back off really fast up to the very last mile of the battery.
So would you describe that as dynamic balancing, that you can do it throughout the charge cycle?
It does it all the time, and it's powered by the PoE. So the controls are powered by the PoE switch, but the actual balancing energy is coming from the highest cell in the pack. So it's continuously doing it as long as the system's connected to the PoE switch.
So there's no need for any absorption or equalization phase for balancing, like top-level balancing might require?
No, you don't need to do that. You can, when you set up your SP Pro for charging, you just set it to a full charge all the way through. You almost couldn't charge the battery too hard. You don't have to limit it. I think the SP Pro limits you to 2 times the, I think it's 2C or 200% of the amp hour rating. But we can tolerate 10C. So that's why you can charge with a DC coupled solar power system if you want to charge much faster. So the fastest we've been able to charge it is 6 minutes so far, and then we get close to the top. As soon as one of the cells goes high, we just tell the inverter to back off and say, stop charging so hard. I can't balance that fast because I don't have that size balancing inside me. We do have a larger size balancer available, which is 10 amp rated, but it starts to get quite expensive if you want to be able to balance that fast.
Yeah. Another follow-up question. So you've shown us the high voltage version, the 147 volt unit, and this one appears to be a 55 volt 12 cell. Do you do any other sizes?
Yeah. So within this range here, I'll just write this here. So the first model we have, if you start on the left over here, is the 6.9 volt model. Which is right here.
Is it the same physical form factor, or is it a small unit?
No, it's just almost the same height. It looks like a. I can pull one up if you need me to, but it's the same. Almost, it's 233 by 210, and it's. It's 665 tall.
So it's a shoebox, but not quite a full cricket stump height.
If you've ever installed a 1,000 amp hour tubular plate lead acid battery, the typical lead acid battery you put in a PV system from the last 20 years. It's the same physical size as that, but it weighs much less. It's only 43 kilos, not 75 kilos. And so we have a range of voltages in that series. We've got 6.9, 9.2, 13.8, 18.4, 27.6, and 55.2. So it's the same module, same number of cells. It's just we parallel and series in a different configuration to get a different voltage outcome. And you can series connect these modules as well. So you can take four of the 13.8s and put them in series, and you end up at 55.2 volts. Or 2 of the 27.6s are 55 volts. Or recently we had a guy who wanted to run from 40 to 57 volts, and it worked out better for him to take 7 of the 6.9s. So he had a really good voltage window to suit his older inverters. His newer inverters couldn't get past 57 volts. So you can be pretty flexible. I had another guy contact us about a 36 volt system, or you could just do 3 of the 13.8s. So
Gotcha.
Basically you can series and parallel any number of these modules to get to the amount of voltage you need and the amount of power you need. These ones are 800 amp fused, so they have very high peak power.
Great. Can we go back to the 3D picture for a second? We've got another question from Bradley, so I'll just bring that one on. So Bradley asks, what happens if you lose communication with the inverter?
So there's a built-in shunt trip inside the MCCB. So we can fire the circuit breaker to turn off, and the boards inside here work autonomously. So within our software, there's 2 processes well, there's one main processor in here, which is a Arduino processor, and it monitors the battery. And if it sees something's wrong, if any cell is outside the voltage window that it wants to be in, or if there's too much power coming through, there's also a current sensor in here, which I haven't shown you yet. I'll just move this other way. Where is he gone?
I just love watching you pull it apart. Oops, turn the outside off.
Just see if I can find him. Where's he gone? He's under there. There he is there. So this is
the current sensor. There. So it's a transducer?
Yeah, it's a 4 to 20 milliamp current sensor, and combined with measuring the voltage inside the Arduino processor board, we can fire a shunt trip into the MCCB and break it off the bus, so it can't take any more power from outside, and then you have to manually reset that. So we did think about having a motorized reset on it, but we don't think it's necessary. Like, it's extremely unlikely we'd ever need to trip the circuit breaker, and if we did, there'd have to be a very good reason for it. So that can happen autonomously, or it can happen remotely via the comm system.
So I think a parallel question, this is me, not Bradley, but thank you, Bradley, is so can your batteries be used without communication cables to a charging source like an inverter or an MPPT?
Yeah, you don't need to have comms to the battery because it's typically more powerful than the inverter could ever push or pull from it. And provided you've constrained the limits of voltage on your inverter, say from, for example, in the lower voltage range, if you made sure you didn't charge past 65 volts, which is pretty easy to do, and didn't go under 35 volts. But even in that, having said that, the UCBs are pretty tolerant to being discharged completely. They don't fail. So they don't fail because of an over discharge. So you can discharge them multiple times to zero and they'll come back again. So you don't have to have any comms from your inverter, but having the comms on the larger one gives us a lot of extra features, like it lets us give the longer warranty because we know that it's being treated properly.
Right. And in terms of temperature, you've done tests at 55 degrees Celsius or 40 something as well. What about low end? How do they perform? At my place where it's sometimes 5 degrees in the morning, or less.
We've only tested down to -10, but the cell manufacturer says the cells are okay to -50. I don't know if that's true or not because I haven't tested it. So we can only go on what we've tested. So we allow -10 up to 60 degrees as the operating range. It doesn't degrade because of low temperatures. You just might lose a little bit of your peak power at the lower temperatures. So -10 is pretty good. You can charge at full power at -10.
That's amazing because most lithium chemistries are a little bit fussy about cold temperature charging, often reducing their charge rate significantly. And certainly in off-grid applications where at wintertime your battery might be flat and cold first thing in the morning and the sun comes up, you really want to capture much of that early morning sun as you can at full power.
Well, that's a really good point. So one of the big pluses of having almost unlimited charge power. So we could, for example, charge this battery in 20 minutes if you had enough available power. In Melbourne, that's really helpful because we have the sun come out for about 45 minutes on some days. And so if you had a large enough solar array and enough sunshine, then you're not really constrained by your charge rate, especially if you're DC coupled. So you could have a very large PV array, say 30, 40 kilowatts and say 30 kilowatt hours of storage. And that sun could come out in full brightness just for 1 hour and you could fill the battery completely. Whereas a lot of other batteries, they need a lot more time. And by the time that time expires, the clouds have come back again. So having very fast charge batteries, which with almost no losses, is a big plus on an off-grid project.
Oh, cool!
But my favorite feature is the longevity. That's by far the cycling, almost unlimited cycling. Like your inverters would fail before your battery failed is an unusual statement to make.
Yes. Actually, that leads me to my next question, which is, does it work with any particular inverters or charge controllers?
It doesn't mind what it is because, again, as long as the inverter doesn't need any comms to make the battery work, that's the main thing. The voltage window on this battery is typically wider than most other batteries. So if you've got a lithium-ion to consider, or a lead acid battery, this has a wider voltage window. So typically you don't have to do any reprogramming, depending on obviously what the inverter was programmed for before. So you can use it on any inverter. But I can't say for longevity, we recommend the electronic inverters because we've used them for a long time now, and they just don't have any failure problems that I've been able to find. And they give us all the monitoring as well. So if we were to log in through Emacs, which you see on screen, which is this little black box on the right that we developed, it's a remote access platform, a little bit like SP, what's it called? Select Live?
Select.live, yep.
Live, yeah, we developed this several years before Select Live was available, and there's a lot of them around Australia and internationally. Having the remote access, having an SP Pro, which is all live, and having the battery on the same platform means you could log in and view your SP Pro data, your battery data, and reprogram everything from one platform, which is very flexible. We're doing some work at the moment with the Queensland government to manage generators in hospitals using the same platform because they want to do energy arbitrage. So there's a lot of new stuff coming along for Emacs that wouldn't be coming along for Select Live, for example, because it's really a one-to-one product, whereas Emacs is a one-to-many product.
Okay. Look, I'm just going to bring us both back on screen. A few more questions. Well, hang on, to bring you on the right. There we go. So would you describe the UCB as a lead acid replacement if someone had a lead acid system that was failing?
Yeah, it's very good for lead acid replacement. In fact, we recently had a guy who paralleled it with a lead acid battery. And now you might have some words to say about circulating currents, but because the UCB lasts so long, this particular person had their lead acid battery was dying and it didn't have the peak power available to run the loads. So adding the UCB in parallel with the lead acid battery, directly in parallel, meant that when the heavy loads came on from the inverter, the UCB delivered the power and the lead acid battery said, I'll give you a little bit, and the UCB said, I'll give you all of it. And then when the load dropped away, the lead acid battery and the UCB equalized again. So it's kind of put a lead acid battery, gave an old lead acid battery new life for a very low cost, because you don't need many of them to do that. In fact, he only added one UCB onto an old lead acid battery bank and meant the guy could get through winter, basically, because he had unlimited power, whereas before he didn't have that. But as far as the question goes, is it a direct replacement for lead acid? Yeah, it is. So you can take your lead acid out and put the UCBs in. You can choose any voltage that suits you, any combination of parallel series, and they fit in the same battery box typically because they look like a 1,000 amp hour lead acid battery.
You haven't got a picture of the smaller form factor one handy there, or I could... I'll just chat while you have a look for it.
Turn off my screen. Just turn off my screen for a second.
It is turned off, yep. So I'm just going to solo myself for a second while you have a look for that. I can see, Bradley, there's some pricing questions. I think we'll leave the pricing questions to Paul directly, not on the live, but you can talk to him about that. He's can be contacted through rvo.com.au, arvio.com.au, and ask about any pricing costs for components. But what I wanted to share, based on what Paul just said about lead acid replacement and paralleling with lead acid, I've done a little bit of experimentation with this with a few different combinations of old lead acid and new lithium, advanced lead acid, the sort of the hybrid supercapacitor, and it's true. There's definitely a way of stretching the legs on a dying lead acid system by paralleling it with you could say a high performance battery. So just to get a bit more scientific about it, I put separate I use the Victron BMVs, the battery monitoring devices, with their own shunts on each of the two battery systems, the lead acid and the lithium, so I could measure the currents during charge and discharge. And there was a little bit of crossover at some point where you would see current going from one battery to another because of impedance differences, but actually it was quite small. And it wasn't dangerous because you are required to have individual string overcurrent protection. So, if you had a very large system where you might get some high currents flowing between the batteries, it can never be such that it could damage one or other. But it did mean that the low impedance you could say high performance lithium was doing most of the work for the first, X% of the state of charge. So you end up putting the lead acid system out to pasture. It was hardly doing any work at all. And it meant for customers who had a failing lead acid system that still was working, but they're not ready to cough up on a whole new battery storage system, it meant you could easily give them a sort of second life, as it were, even a way of sliding off lead acid onto lithium progressively. I mean, it's not unique to any particular type of lithium. Many self-managed lithiums can do this, but it is a nice feature to have, that you can parallel the two together. You've got to be aware that there will be voltage limits for both types of batteries, both high and low, and you've got to stay within those parameters for both of them, and that may be a compromise, certainly in terms of, are you adequately balancing the lithium batteries? If they're top balanced, for instance, are you going high enough? In the case of the UCB, not a problem, because they do dynamic balancing throughout their charge cycle. And with the lead acid, are you undercharging the lead acid because the lithium might have a lower peak voltage than, say, a flooded lead acid battery system? But the caveat given there, as long as you're within the reasonable parameters for both of those, it's quite doable. Now, I can see in my little side window, Paul's looking for some pictures. Just let us know when you're ready, Paul.
I've got one here. Yep.
Okay. Happy to bring that on?
Yep.
All right. I'm just going to bring... So Paul's got a picture of an installed system here. There we go.
Okay, this is just recently commissioned. This is 20 by 2.2 kilowatt hour modules, and each of these is 13.8 volt DC. You can see there's 10 in a row. So 10 by 13.8 is 138 volts, and that's the second row behind. So here we have 44 kilowatt hours of storage, sits on the floor, connects up to a DC MCCB here. We also have two iMark charge controllers. They're made locally in North Melbourne, so a big plug for Owen at iMark. He developed this 500 volt DC input, dual MPPT, 15 kilowatt DC charge controller, which is paralleled onto the DC bus here. So that's our energy source. Up the top here, you can see the solar panels. It's 20 kilowatt hours worth of storage, 20 kilowatt hours worth of PV, feeding into 5 MPPT strings on these two charge controllers, 2 in parallel and 1 each for the other ones. And then they've got the 15 kilowatt SP Pro on the left over here. So this is a whole turnkey system. The Emacs you can see on the bottom here behind the 4G modem, and then just your power board on the left over there. So that's a typical installation, off-grid, tons of power, 30 kilowatt AC peak, 15 kilowatts continuous, 20 kilowatts of PV with 20 kilowatts worth of charge control power. So this 44 kilowatt hour battery can charge in about 2 and a bit hours from empty to full. And if we start a generator up and run it through the SP Pro, if we had, say, a 15 kilowatt AC generator, we could charge it 15 kilowatts DC onto this bank, along with the PV of 20 kilowatts, which is 35 kilowatts of power, which would charge a 44 kilowatt hour bank in about an hour and 10 minutes or so. So that's a very simple, elegant system with a lot of power and a lot of simplicity. And in this case,
indeed.
Yeah, it's just very simple to install. You basically, each of the modules is just paralleled internally with series connected internally with copper bus bar. And this is 1600 amp rated, so 2 rows of 800.
I was going to ask, you can't see any intercell connections at all, so it's all done through a internal copper bus bar between the cells.
Yeah, it's a copper tube actually, and the balancing wire passes through the tube. So it's all very simple and hidden, which means you don't have to put a battery enclosure around it because everything's there's no touchable terminals.
Yeah, yep. So you'll still have to consider the local environment, like if that's in a garage and there's an impact zone, there'll be other considerations. This looks like it's a dedicated room in a shed, not a garage. Yeah.
Yeah.
Wow. This picture and those specs just make me realize that everything we've talked about in the world of off-grid design, which I run courses in all the time, were based on the days when PV was very expensive. PV was quite small. You sized things just enough to do the job, and you tried to afford enough battery storage to get you through 4 or 5 days of bad weather, and let that small PV system recharge your battery pack. But now with low costs of PV, falling costs of storage, and oversizing of PV significantly compared to what notionally you might require, you can do what Paul just described, which is do a really fast charge with a large PV system. So you can really pack that power in if you've got the right type of battery and the right size PV system.
This one on screen now, Glenn, can you see that okay?
I'll bring that one back up.
This one's an all-in-one cabinet we built. We call it IDS, the Independence Day system. So this one here is a computer rack cabinet, which is 0.6 by 1 meter by 2 meters tall. And it's got in the back 6 UCB, so it's 13.2 kilowatt hours, and then enough room to put another 6 up here. So this would be 26 kilowatt hours of storage on this product. It comes delivered with the inverters in the front, cooling fans on the top, and this little box here which you screw to the wall with your loom. So it's got your PV coming in here, your AC from your generator, and your AC out to your site. And it looks like this on the front.
So it's just lying on the ground because it's on a pallet, but normally that would be attached to a wall with the tether. Yep.
That's right. And it's on casters. So you basically, this is delivered to site on a pallet, and you put it on the ground, and you plug in your generator to that box on the left, your PV to the box on the left, and your loads to the box on the left, and then everything else is switched on through here. A very simple system, packed up and shipped off like that. So if you don't want to build your systems on site and risk forgetting that you've got a lug that you forgot to buy, or a screw or something, this is all prefabbed and pre-tested and dispatched, and has remote access built in as well. So you just plug in a 4G modem. Clients typically have a 4G modem on site, remote access wise, so we just plug into that. There's no remote access setup required. You just plug it in and go home, and then you have remote access immediately available to you.
Wow. Look, I'm seeing a big trend in the industry towards pre-built solutions for lots of reasons, but this is a strong one, which is for off-grid installers, doing all this on site, taking all those components and hoping that you've got every lug that you need to some remote area and assembling it is a recipe for disaster. But pre-built. Yeah. It also really helps with the cost of from the perspective of quoting. You basically have embodied all the cost of building that system right there in your factory. So really, the installer can quote fairly confidently. They're not going to go, oh, gee, I need to put a new backing board in there, and there's not room for the batteries. As long as you've got a room for that cabinet, you're good to go.
Yeah, it makes it much less risky on site. And the further you go away remotely, the more that costs if you make a mistake. So being able to be sure that you can just drop it on site, plug in your PV, plug in your generator, and plug in your house, and go home and remotely view it on your SP Link. So you can log in through SP Link and reprogram it, adjust it, see that it's working okay. We've got alerts available through the Emacs platform as well, so you can get an email to say something's wrong. So we're really heading towards a turnkey solution that makes off-grid really maybe even simpler than on-grid. If you've ever tried to connect a house, but as we're building passive houses, connecting to the grid is actually a lot of work. A lot of phone calls, setting up CESs for inspecting underground cabling, and then adding meters and outdoor meter enclosures. It's actually probably easier now just to go off-grid, depending on, obviously, how much PV you can get on the roof.
Yeah, it's becoming a very viable choice. Certainly fringe of grid, if there's not power to the site already, the cost competitiveness of standalone is there already, in my mind. Yeah. So, Paul, we're nearly at the top of the hour now, and we've covered a lot of territory here. If people want to follow up with you on any of the stuff we've talked about, what's the best method?
They can just send through an email to info@arvio.com.au. Or you can send it to me personally at paul.wilson@arvio.com.au, and just see if we can help you with your project. So we can either sell just the batteries, or we can sell the Emacs or a turnkey system on a pellet that you can build yourself, or we can pre-assemble it as an IDS where you just wheel it onto site and then do the things you like to do, which is add the solar panels to the roof and connect it to the client switchboard. So we do all levels of support and supply. We also have Steve Crocker, one of our engineers, on standby as well. So if you're new at sell electronic inverters for programming, we can log in remotely and support you, help reprogram the system and check it. We do that quite a lot. So the Emacs platform gives us that real ability to give great support to our installers.
Cool. Well, thanks very much, Paul. Really appreciate taking some time on your weekend to talk to my audience here at the Toolbox Tech Talk.
Yeah, it's been great. Well, appreciate it.
No worries. All right. Well, we'll just say goodbye. See you, Paul, and I'll just do the outage.
Great. Thanks very much, Glenn.
Yeah. Well, thanks everyone for attending another Toolbox Tech Talk here at the Smart Energy Lab, live on Facebook, YouTube and Twitter. I'm actually running a course next week, so I'm teaching for 5 days in a row solar and battery storage. It's something I've been doing every other week lately. There's such a lot of demand. Because of the lockdowns here in Melbourne, I haven't been able to run face-to-face courses, but it turns out that actually delivering via Zoom to a classroom where people interact with each other and myself directly works really well. So if you're interested in any of those courses, just go to solarquip.com. That's solarquip.com, one word, or solarquip, one word.com, and you'll see the courses advertised there. Otherwise, I'll see you back next Sunday at 2 p.m. for another Toolbox Tech Talk. And thanks everyone for your comments. And Bradley, you get 4 gold stars for asking lots of questions. Thank you very much. Okay, and we're out.